Andromeda, our nearest galactic neighbour, 2.5 million light-years away. What secrets does it hold, and what would it mean for us when it finally collides with the Milky Way? In this documentary, we'll journey across the void to explore Andromeda's stars, black holes and mysteries. If you enjoy cosmic adventures, please like, subscribe and share, and tell us in the comments what fascinates you most about Andromeda. Thank you for watching. Now, let's begin. The Andromeda Galaxy comes into view as a wide, soft glow stretched across the night sky, larger in angular size than the Moon, though far fainter to the human eye. It is located at a distance of about 2.5 million light-years from the Milky Way, so the light that reaches Earth today began its journey long before humans, or even most familiar species, appeared on our planet. Through even a modest telescope, Andromeda shows itself as an elongated oval patch of brightness, with a concentrated centre that gradually fades into a halo of light. The long axis of this oval is not a true shape, but rather the result of our angle of view. The galaxy is tilted with respect to our line of sight, so the circular disk appears foreshortened. This slant allows astronomers to see not only the bright inner region, but also the faint outer disk, which is lined with dust and stars extending far beyond the central glow. The core of Andromeda is striking in its brightness. At its centre lies a compact bulge dense with older stars that radiate a yellowish light. Around this bulge stretches the broad disk of the galaxy, flattened like a giant rotating plate of stars and gas. Along the disk, two dark streaks stand out. These are prominent dust lanes. They are not truly voids, but rather regions where interstellar dust absorbs visible light, blocking the glow of stars behind them. The lanes give texture to the galaxy's light, and are especially noticeable in long-exposure images taken with modern telescopes. To the eye through an eyepiece, they appear as shadows across the otherwise uniform brightness. Astronomers have measured Andromeda across many wavelengths, from radio waves to infrared to ultraviolet. Each range of light highlights a different part of the galaxy. In visible light, the grand spiral pattern is subtle, because much of the disk's glow comes from older stars. In the ultraviolet, however, the young blue stars shine intensely, tracing out the curved spiral arms and the large star-forming ring that encircles the inner disk. Infrared light, less affected by dust, reveals the smooth spread of cooler older stars that dominate the stellar mass. Radio telescopes map the neutral hydrogen gas that extends well beyond the visible disk, outlining a warped outer structure that is far larger than the glow seen in ordinary images. The scale of Andromeda is immense. The galaxy's stellar disk stretches across more than 200,000 light-years, roughly twice the size of the Milky Way's visible disk. Within this span are hundreds of billions of stars, countless clouds of gas and dust, and a complex network of star clusters and stellar streams. Despite this enormity, the central region dominates what we see from Earth. The bulge is compact but highly luminous, and it gives the galaxy its characteristic bright core. As the distance from the centre increases, the light gradually thins first to the spiral arms, and then into the faint outer halo where individual stars can still be detected in modern surveys. The brightness of Andromeda made it known to humans long before telescopes existed. Ancient astronomers recorded a small fuzzy patch in the sky, in the constellation of Andromeda. The Persian astronomer al-Sufi described it in the 10th century as a small cloud. With the invention of the telescope in the 17th century, observers were able to see its extended shape, though its true nature remained unclear. It was called a nebula, a word meaning simply a cloud-like object, since at that time astronomers did not yet know whether these faint patches were within the Milky Way or separate systems altogether. Only in the 20th century, with the discovery of Cepheid variable stars within the object, was its true distance measured, confirming that Andromeda is an entire galaxy outside our own. From Earth today, the view is enhanced by digital detectors, large ground-based observatories and space telescopes. Long exposures reveal extraordinary detail such as knots of star-forming regions and fine filaments of dust. The galaxy is oriented so that one edge is tilted toward us, creating the illusion of depth as the spiral arms curve away. The tilt is about 77 degrees, meaning we view the disk almost edge-on but with enough angle to see its internal spiral structure. This perspective has advantages. It allows astronomers to trace the distribution of gas and stars vertically above and below the disk plane, and to measure how the disk is warped at its edges, likely due to gravitational interactions with companion galaxies. The dust lanes that cut across the disk are particularly striking. These lanes are composed of grains of carbon silicates and other heavy elements that absorb visible light. Behind them, bright clusters of stars shine, creating sharp contrasts. In photographs, they appear as dark filigree against the galaxy's glow. Yet in infrared images, the dust glows itself, warmed by starlight, and re-radiating in longer wavelengths. These dual images, one showing absorption and the other showing emission together, outline the complex interstellar medium that threads through the galaxy. The dust and gas are not merely obstacles to light, but are also the raw materials for new stars, and their distribution strongly influences the future of star formation in Andromeda. The disk is not perfectly flat. Observations of neutral hydrogen with radio telescopes show that the outermost regions bend and twist slightly, a warp that is common in large spiral galaxies. Such distortions suggest that external gravitational forces are at work. Companion galaxies such as M32 and M110 exert steady pulls, and past mergers with smaller galaxies may have left lasting imprints on the structure. These features are visible only through careful mapping, yet they remind us that the galaxy is not static. Stars' gas and dark matter interact over cosmic timescales to maintain the overall disk, while producing subtle deviations in shape. Even though Andromeda is visible to the naked eye from dark locations, its full glory is revealed only through sensitive instruments. The human eye collects light for only a fraction of a second, while a camera on a telescope can gather light for hours, building up an image far deeper than natural vision allows. Such images show star clusters scattered across the disk, bright knots of emission nebulae where young stars energize surrounding gas, and faint stellar streams looping outward into the halo. Each of these features adds to the portrait of a galaxy, both familiar in its spiral structure and unique in its specific details. Astronomers continue to refine measurements of Andromeda's structure and light. Gaia, the European space mission that measures stellar positions and motions with high precision, has provided detailed maps of individual stars even in this distant system. Combined with surveys from the Hubble Space Telescope and ground-based observatories, a layered picture emerges: a luminous bulge, a wide disk, spiraling arms lined with dust and star-forming regions, and an extended halo reaching far into intergalactic space. At the scale of human life, Andromeda appears unchanging. Yet behind the calm glow lies a record of dynamical processes, gravitational influences, and the continuous cycle of star birth and death that define its character. The global structure of the Andromeda Galaxy reveals itself gradually as astronomers measure its shape and motions across many wavelengths. At its broadest level, Andromeda is a large spiral galaxy composed of a stellar disk, a central bulge, spiral arms, and an extended halo of stars and dark matter. The stellar disk is vast, stretching across more than 200,000 light-years, making it one of the largest members of the local group. This disk is not simply a flat, featureless plane. It contains a layered arrangement of stars, gas, and dust, with the densest parts concentrated toward the inner regions. The central bulge dominates the innermost portion, while the spiral arms mark the outer zones where ongoing star formation takes place. Beyond the visible light of the disk lies a halo of old stars and globular clusters, extending into space where its edges merge with intergalactic darkness. The bulge itself is a compact spheroidal region filled with older, redder stars. These stars orbit in random directions rather than in the ordered rotation of the disk. Their light gives the central region a yellowish appearance, contrasting with the bluer tones of young stars in the outer disk. The bulge is thought to have formed early in the galaxy's history, either through rapid star formation in the young Andromeda or through the merging of smaller protogalactic fragments. Its density and brightness are so high that it dominates the light profile of the galaxy, accounting for much of the glow seen from Earth. Surrounding this bulge is the broader stellar disk, which rotates as a whole around the centre. The rotation speed remains high, even at great distances from the centre, an observation that implies the presence of dark matter in quantities exceeding the mass of visible stars and gas. The spiral arms of Andromeda are more complex than a simple two-armed pattern. Observations in the infrared, radio, and ultraviolet reveal multiple arm segments and a large star-forming ring. The arms are not rigid structures, but density waves regions where gas clouds are compressed as they orbit the galactic centre. Within these compressed zones, gas collapses to form new stars which then light up the arms with their brightness. The blue colour of these young stars makes the arms stand out against the redder disk. Nebulae rich in hydrogen gas also trace the arms, glowing in pink and red emission, where young stars ionize the surrounding material. Thus, the spiral arms are both sites and indicators of stellar birth. The star-forming ring, located about 30,000 light-years from the centre, is a prominent feature of Andromeda. It is a nearly circular zone where the density of gas is higher than in the surrounding disk. The presence of the ring is often explained as a resonance feature created by the gravitational influence of a central bar structure that channels gas inward and outward at specific orbital radii. Where the resonances occur, gas collects, forming a dense ring where star formation proceeds vigorously. The ring is visible in ultraviolet and infrared images, showing the mix of hot young stars and cooler dust warmed by their radiation. It stands as a signature of dynamical processes within the galaxy, a sign that internal structures shape the flow of material across vast distances. The disk of Andromeda is not perfectly symmetric. Careful measurements show that it is slightly warped, with its outer regions bending above and below the central plane. The warp is mapped most clearly in neutral hydrogen gas, which extends beyond the visible stars. The distortion is thought to result from tidal interactions with nearby companion galaxies such as M32 and M110, or from the remnants of past mergers with smaller systems. These interactions stir the outer disk, producing long-lived waves and asymmetries. The warp does not disrupt the overall stability of the galaxy, but it adds a layer of complexity to its structure, demonstrating that large galaxies are shaped continually by gravitational encounters. The halo of Andromeda adds another dimension to its global form. Composed of old stars, globular clusters, and large amounts of dark matter, the halo extends hundreds of thousands of light-years beyond the visible disk. The stars in this halo are sparse, but deep surveys have traced them far from the centre. They provide evidence for Andromeda's history of accretion, since many halo stars and clusters appear to have originated in smaller galaxies that were absorbed long ago. The globular clusters in particular serve as ancient fossils with ages often exceeding 10 billion years. Their distribution forms a spherical envelope around the galaxy, reaching outward into space far beyond the luminous disk. Modern surveys such as the Pan-Andromeda Archaeological Survey have mapped the halo in detail, revealing tidal streams, shells, and other structures left behind by disrupted satellites. These features demonstrate that the global structure of Andromeda is not a simple, smooth system, but rather the result of ongoing assembly. Each new survey adds to the complexity of the picture, showing how the disk, bulge arms, and halo are interwoven with evidence of past interactions. The global structure is therefore not static. It reflects the accumulated history of star formation mergers and gravitational influences over billions of years. The orientation of Andromeda in the sky provides a unique opportunity for astronomers. Its tilt of about 77 degrees allows us to view both the broad disk and the vertical structure above and below it. From this perspective, the dust lanes stand out clearly silhouetted against the bright starlight of the bulge. The spiral arms can be traced even in visible light, though they are most striking in ultraviolet and infrared. The warp of the outer disk becomes apparent in radio observations. By combining these different perspectives, astronomers have built a three-dimensional model of the galaxy's structure, including the thickness of the disk, the extent of the bulge, and the reach of the halo. The distribution of mass within this structure is another key feature. Measurements of stellar and gas motions reveal that visible matter accounts for only a small fraction of the total mass. The rotation curve, which plots orbital speed against distance from the center, remains nearly flat far into the outer disk. This flatness indicates the presence of a massive dark matter halo surrounding the galaxy. Estimates of the total mass vary, but most place it in the range of several trillion times the mass of the Sun. The dark matter halo therefore dominates the global structure, binding the disk, bulge, and halo stars within its gravitational grip. In summary, the global structure of Andromeda is layered and dynamic. A luminous bulge filled with old stars anchors the center. A rotating stellar disk decorated with spiral arms and a star-forming ring spreads outward. Dust lanes and gas clouds mark regions of active star formation. A warped outer disk testifies to tidal encounters. An extended halo of stars, clusters, and dark matter surrounds the whole system, stretching far into intergalactic space. The scale of this structure is vast, yet each part is connected, and each observation adds to a coherent picture of a galaxy that is both stable in its overall form and constantly shaped by the processes of cosmic evolution. At the heart of the Andromeda Galaxy lies the bulge, a dense and luminous region that dominates the central light profile. The bulge appears round in projection, glowing with the steady light of countless old stars. These stars are generally lower in mass and cooler than the younger stars found in the spiral arms, giving the bulge a yellowish hue when observed in visible light. Their orbits are not neatly aligned like those in the disk, but are instead distributed in many directions, creating a spheroidal swarm. This randomness produces the dense appearance and explains why the bulge seems more compact and concentrated than the surrounding disk. Studies of the bulge reveal not only its stellar content but also its complex structure, which includes evidence for a central bar nuclear clusters and even a double nucleus. The idea of a bar in Andromeda arises from infrared observations that cut through obscuring dust. In visible light, the bright starlight of the bulge overshadows finer details, but in the infrared, where cooler stars and stellar distributions are easier to trace, a stretched central feature emerges. This elongated bar appears to align with the galaxy's major axis, extending across the inner few thousand light years. Astronomers interpret the bar as a common structural element in large spiral galaxies. Bars form when the disk's stellar motions become organized in such a way that gravity amplifies a central elongation. Once established, the bar channels gas toward the center, where it can accumulate and fuel star formation or feed the central black hole. In Andromeda, the bar's influence is linked to the star-forming ring farther out in the disk, since resonances created by the bar's gravity define the boundaries where gas piles up. Thus, the central bar, though subtle in appearance, plays an important role in the galaxy's overall dynamics. Closer to the very core, high-resolution images from the Hubble Space Telescope reveal an even more surprising structure, the double nucleus. Instead of a single peak of starlight at the very center, the light distribution shows two distinct bright spots, separated by only a few light years. This was initially puzzling, since one would expect the black hole at the center to anchor a single dense cluster. Detailed analysis, however, demonstrates that the double nucleus is an illusion produced by an eccentric stellar disk. In this configuration, stars orbit the central black hole along elongated paths. Because many of these orbits align in the same orientation, the stars spend more time at one end of their ellipses, creating a brighter region offset from the true center. The second fainter peak corresponds to stars near the opposite end of their orbits. The black hole itself lies near the fainter of the two peaks. This discovery highlights the subtlety of galactic dynamics, where collective motions of stars can create apparent structures that mask the underlying cause. At the very core of this system sits the central black hole, a massive object whose gravity governs the orbits of stars in its immediate vicinity. By measuring the motions of stars near the nucleus, astronomers estimate the mass of the black hole to be on the order of 100 million times the mass of the Sun. This places it among the more massive central black holes in nearby spiral galaxies. Unlike the supermassive black holes in some active galaxies, however, Andromeda's black hole is relatively quiet. It does not produce strong jets or luminous accretion disks at present. The lack of bright activity suggests that little gas is currently falling into it. Nevertheless, its influence is evident in the rapid stellar motions within the innermost parsec, where velocities reach hundreds of kilometers per second. These measurements provide some of the clearest evidence that nearly all large galaxies harbor central black holes tied closely to their bulges. The stars of the bulge carry a record of Andromeda's early history. Spectroscopic studies show that many are old, with ages exceeding 10 billion years. Their chemical compositions reveal high metallicity, meaning they contain substantial amounts of elements heavier than hydrogen and helium. Such enrichment indicates that the bulge experienced intense and rapid star formation in its youth, with many generations of stars producing heavy elements through nuclear fusion and supernova explosions. Later generations inherited this enriched gas, leading to the metal-rich populations seen today. The concentration of these stars in the central region supports theories that bulges form quickly during the early assembly of galaxies, possibly through mergers of dense clumps or through rapid collapse of gas into the central potential well. The structure of the bulge is not perfectly spherical. Observations show that it is somewhat flattened and may contain substructures beyond the central bar. Some models suggest the presence of a boxy or peanut-shaped component, features that often arise when bars thicken vertically over time. The interplay of these elements, the classical bulge, the bar, and the nuclear disk, demonstrates that Andromeda's inner structure is layered and complex. Each component likely formed under different circumstances, yet together they create the luminous core we observe. Astronomers study the bulge not only in light, but also through stellar kinematics. Spectrographs attached to large telescopes disperse the light of the bulge into spectra, allowing measurement of Doppler shifts that reveal the velocities of stars along the line of sight. These measurements show broad ranges of velocity, confirming that the stars move in random orbits rather than in a coherent rotation. By modelling these distributions, scientists can estimate the mass contained within the bulge, including the contribution of both visible stars and the central black hole. Such measurements help calibrate theories of galaxy formation and connect the growth of bulges to the growth of black holes. The bulge also interacts with the disk around it. Gas funneled inward by the bar or by spiral arms often collects in the central few thousand light years. There it can compress and form new stars, adding younger populations to the otherwise old bulge. Evidence of recent star formation near the nucleus comes from clusters of young hot stars detected in ultraviolet light. These stars are few compared to the billions of older stars, but their presence shows that the central environment is not entirely static. The balance between inflows of gas and the energy output of stars in the black hole determines how active the bulge remains. In Andromeda, the current state is relatively quiet, but even low levels of activity leave signatures in the stellar content. The double nucleus in particular provides a natural laboratory for understanding such dynamics. Few galaxies in the nearby universe show such a clear example of an eccentric disk of stars orbiting a massive black hole. By analysing the light and motion of the stars in these two peaks, astronomers can refine models of how stellar systems behave under strong gravitational influence. The lessons learned extend beyond Andromeda, offering insight into the inner workings of galactic centres in general. From a broader perspective, the bulge and its features emphasize how galaxies are not simple disks of stars but layered structures with histories imprinted in their light. The luminous bulge, the subtle bar, the eccentric nuclear disk, and the massive black hole together form a nested hierarchy of structures, each shaping the evolution of the galaxy at different scales. Through steady observation and careful analysis, astronomers have uncovered this complexity step by step, turning what once appeared as a simple bright core into a dynamic region filled with clues about Andromeda's past and present. The spiral arms of the Andromeda Galaxy are among its most recognizable features, though their appearance depends strongly on the wavelength of light in which they are viewed. In visible light, the arms are less obvious than in some other galaxies, because much of the disk is dominated by the steady glow of older stars. Yet when observed in ultraviolet light, where hot young stars shine brightly, the arms trace out curved arcs that wind around the central bulge. These arcs are studded with clusters of blue stars and bright knots of glowing gas, evidence of ongoing star formation. The arms are not physical objects that rotate with the stars, but are instead density waves, large-scale patterns that move through the disk more slowly than the stars themselves. As gas clouds encounter these regions of higher density, they are compressed, triggering gravitational collapse that leads to the birth of new stars. The process creates a self-reinforcing cycle in which young stars illuminate the very regions where they formed, making the spiral arms visible across great distances. One of the most striking structures within the disk of Andromeda is the star-forming ring that encircles the inner regions at a radius of about 30,000 light-years. This ring is not perfectly circular, but appears slightly offset from the galaxy's centre, suggesting that gravitational forces have influenced its shape. The ring glows brightly in infrared images where heated dust reveals regions of active star formation. Observations from the Spitzer Space Telescope and later from the Herschel Space Observatory highlight the distribution of warm dust within the ring mapping areas where massive young stars have recently formed. In ultraviolet, the ring is equally clear with patches of bright blue light tracing the youngest and hottest stars. The ring's presence indicates that dynamical resonances within the galaxy are shaping the flow of gas-guiding material into regions where it accumulates and collapses. The connection between the central bar and the star-forming ring has been the subject of careful study. Bars act as engines of redistribution within galaxies. Their elongated gravity fields create resonances where orbital motions of stars and gas align in particular ways. At these resonances, gas tends to accumulate, forming rings. In Andromeda, the outer Lindblad resonance associated with the bar is thought to coincide with the location of the star-forming ring. Gas driven inward by the bar piles up at this radius, increasing in density until it becomes unstable to collapse. The result is a nearly continuous belt of star formation, a prominent feature that distinguishes Andromeda from many other spirals. Within the spiral arms themselves, star formation is not uniform. Large stellar associations form in clusters, often grouped in complexes several hundred light-years across. These complexes contain massive stars whose intense radiation ionizes surrounding hydrogen gas, producing H2 regions that glow in characteristic red light. The Orion Nebula in the Milky Way is a small example of such a region, but in Andromeda the scale is vastly greater. Entire arcs of the spiral arms are lined with emission nebulae, each marking the site of recent stellar birth. Radio observations of carbon monoxide trace the molecular clouds from which these stars emerge. The alignment of these clouds with the spiral arms reinforces the density wave model, as the arms serve as organizing structures for the interstellar medium. Dust lanes thread through the spiral arms, creating dark filaments against the luminous background of stars. These lanes are not empty, but filled with microscopic grains of carbon and silicate which absorb and scatter visible light. Their presence adds contrast to the arms, outlining their shapes with shadow. Infrared observations reveal the same dust lanes glowing softly, warmed by starlight. The dual images of absorption and emission highlight the complex role of dust, both obscuring and revealing star formation. Dust is not merely an obstacle, but a vital ingredient in the process, since molecules form on grain surfaces, and cooling by dust emission allows gas to collapse more efficiently. The distribution of stellar ages across the arms and ring provides further insight. Young massive stars live only a few million years, far less than the time it takes to orbit the galaxy. Their concentration along the arms means they must have formed there recently. Older stars, by contrast, drift away from the arms as they age, populating the general disk. This age segregation creates the color contrast between the blue arms and the yellow disk. Ultraviolet surveys show the sharp delineation of the youngest populations, while infrared maps display the smoother background of older stars. Together, these surveys produce a layered image of the galaxy's structure. The star-forming ring is particularly important because it is not a common feature in all galaxies. Its nearly continuous arc of star formation suggests a stable, dynamical configuration. Some astronomers propose that past interactions with companion galaxies may have enhanced the ring, disturbing the disk and setting up waves that continue to shape star formation today. Others emphasize the role of the bar and its resonances. The precise origin remains debated, but the observational evidence is clear. The ring is a major site of current activity, producing many new stars and clusters. Its brightness in both ultraviolet and infrared makes it a key target for space telescopes, offering a window into the processes that govern star formation on galactic scales. The spiral arms extend well beyond the star-forming ring, curving gracefully into the outer disk. In these regions, star formation becomes sparser and the stellar populations grow older. The arms here appear less distinct, blending gradually into the halo of the galaxy. Yet even at these great distances, pockets of gas remain, and occasional star formation occurs. Radio surveys of hydrogen gas show that the disk continues far beyond the limits of the visible stars, warped and twisted into irregular shapes. These outer reaches remind astronomers that galaxies are not sharply bounded objects, but fading systems whose components extend into the surrounding medium. Andromeda's spiral arms also host many star clusters. Open clusters, loose groups of young stars formed from the same cloud, dot the arms like pearls on a string. Their ages range from a few million to a few 100 million years, representing successive generations of star formation. By measuring their colours and brightness, astronomers can reconstruct the timeline of star formation across the disk. The patterns reveal waves of activity moving outward, shaped by both internal dynamics and external influences. The clusters are laboratories for understanding stellar evolution, as their shared age and composition make comparison straightforward. Overall, the arms and star-forming ring highlight the dynamic character of the Andromeda Galaxy. They demonstrate that galaxies are not static star collections but evolving systems where gravity, gas dust, and stellar feedback combine to produce ongoing activity. The arms trace density waves. The ring marks a resonance with the central bar, and the nebulae and clusters show where new stars are born. Through careful observation across the electromagnetic spectrum, astronomers build a coherent picture of these processes, revealing Andromeda as both a grand spiral galaxy and a living environment of continuous creation. The gas and dust that thread through the Andromeda Galaxy form the interstellar medium, the raw material from which stars are born, and the canvas against which galactic structure is painted. Observations across the spectrum show that this medium is complex and layered, consisting of neutral hydrogen, ionized hydrogen molecular clouds, and networks of dust. Together, these components trace the cycles of star formation and stellar feedback that give the galaxy its evolving character. In visible light, dark lanes of dust cut across the luminous disk, silhouetted against the bright background of billions of stars. These lanes are composed of tiny grains of carbon and silicate, measuring only fractions of a micron across, yet when spread over thousands of light years they block a significant fraction of light. The most prominent dust lanes arc through the disk, aligned roughly with the spiral arms, where gas and dust are concentrated by density waves. Their shapes and contrasts provide clues to the structure of the underlying spiral pattern, as well as to the locations of star-forming regions hidden within. Neutral hydrogen is the most abundant component of the interstellar medium. It is detected primarily through the emission of radio waves at a wavelength of 21 centimeters, a signature of the spin-flip transition in the hydrogen atom. Radio telescopes mapping this line reveal that the disk of neutral hydrogen in Andromeda extends far beyond the visible stars, reaching to radii greater than 200,000 light-years. This extended distribution is not smooth. Instead, it shows warps, twists, and asymmetries, evidence of gravitational interactions with satellite galaxies and the influence of the dark matter halo. The neutral hydrogen traces the large-scale structure of the disk, and its rotation curve provides crucial information about the mass distribution of the galaxy as a whole. Closer to the spiral arms and the star-forming ring, the gas transitions into molecular form. Molecular hydrogen itself is difficult to observe directly under most conditions, but tracer molecules such as carbon monoxide emit strong lines in the millimeter portion of the spectrum. Observations with facilities such as the Atacama Large Millimeter and Submillimeter Array detect these lines and map the locations of giant molecular clouds within Andromeda. These clouds are immense structures, often spanning dozens of light years and containing hundreds of thousands of solar masses of gas. Within them, regions of higher density collapse under gravity to form new stars. The molecular clouds are therefore the nurseries of star formation, and their distribution across the spiral arms and ring highlights where new stellar generations are emerging. Ionized hydrogen, designated H, marks the places where massive young stars illuminate their surroundings. The ultraviolet radiation from these stars strips electrons from nearby hydrogen atoms, producing glowing regions of ionized gas that shine in characteristic red emission. These H2 regions are among the most visually striking features in images of Andromeda, appearing as pink knots along the arms. Each region represents a cluster of newly formed stars, often dominated by a few very massive members that will live only a few million years before exploding as supernovae. Their short lives make them excellent markers of recent star formation, and their distribution helps astronomers trace the ongoing activity within the galaxy. The dust mixed with the gas not only obscures light, but also shapes the thermal balance of the interstellar medium. Dust grains absorb ultraviolet and visible photons, re-radiating the energy in the infrared. Infrared observations from the Spitzer Space Telescope and the Herschel Space Observatory show the dust glowing across the disk and the ring, providing a complementary view to optical and ultraviolet surveys. The brightness of this emission reveals the locations of warm dust heated by young stars, while longer wavelength observations detect cooler dust spread more diffusely. These infrared maps demonstrate that dust is ubiquitous, filling not only the bright star-forming regions, but also extending across the wider disk. The interplay between gas and dust is a dynamic process. Stars form in molecular clouds, and their radiation and winds shape the surrounding medium. Supernova explosions inject energy and heavy elements back into the interstellar gas, creating hot bubbles and driving turbulence. This feedback regulates the pace of star formation, preventing the gas from collapsing too rapidly. In Andromeda, as in other galaxies, the balance between compression in the spiral arms and disruption by stellar feedback creates a patchwork of regions at different stages of the cycle. Some clouds are just beginning to collapse, others are actively forming stars, and still others are being dispersed by the energy of young stars. Studies of the chemical composition of the gas and dust in Andromeda reveal gradients across the disk. The inner regions tend to be more metal-rich, meaning they contain higher proportions of elements heavier than hydrogen and helium. This enrichment results from many generations of star formation, in which supernovae and stellar winds return heavy elements to the interstellar medium. In the outer disk, where star formation has been less intense, the metallicity is lower. This gradient provides insight into the history of the galaxy, tracing how star formation and enrichment have proceeded over billions of years. The gas and dust also interact with the larger gravitational field of the galaxy. The warp of the neutral hydrogen disk suggests that external forces are constantly at work. Interactions with satellite galaxies can stir the outer gas, producing streams and asymmetries. Evidence for such processes is seen in the extended features of Andromeda, where faint arcs of gas and stars trace past encounters. These interactions not only disturb the disk, but also feed new material into the interstellar medium, providing fresh fuel for star formation. Advanced surveys have provided a comprehensive view of the interstellar medium in Andromeda. The HI surveys map the neutral hydrogen distribution with high resolution, while millimeter-wave telescopes chart the molecular clouds. Infrared missions trace the dust, and optical and ultraviolet telescopes reveal the ionized gas and young stars. By combining these datasets, astronomers construct a detailed model of the cycle of gas in the galaxy. The process begins with diffuse hydrogen in the outer disk, collects into molecular clouds in the spiral arms-formed stars within dense cores, and is then returned to the medium by stellar feedback. This continuous recycling sustains star formation over billions of years, maintaining the luminous character of the galaxy. The interstellar medium in Andromeda is not evenly spread, but forms a tapestry of structures on many scales. Filaments of dust win through the arms, giant clouds of gas dominate star-forming complexes, bubbles of ionized gas expand into the surrounding medium, and diffuse hydrogen fills the outer disk. Each of these components plays a role in shaping the appearance and evolution of the galaxy. They are observed not in isolation but in combination, each wavelength highlighting a different aspect of the whole. Together they reveal a living system in which stars and gas are continually linked, bound by gravity, and influenced by feedback processes that span from the smallest clusters to the entire disk. Through this intricate medium, astronomers gain insight into both the present state of Andromeda and the long history of processes that built it. The gas and dust that we see today are the products of many previous generations of stars enriched and dispersed, recollected and reformed. They remind us that galaxies are not static accumulations of stars, but dynamic environments where matter cycles endlessly between different states. In Andromeda, this cycle continues across the vast disk, visible in every dust lane, every glowing nebula, and every cold molecular cloud. The very centre of the Andromeda Galaxy contains structures that reveal the extreme conditions that govern galactic nuclei. What appears from a distance as a single bright point is in fact a layered system with multiple components. At its core lies a supermassive black hole estimated to hold about 100 million times the mass of the Sun. Surrounding this black hole is a dense cluster of stars arranged in an eccentric disk. This configuration produces the unusual appearance of a double nucleus, in which two bright peaks of starlight can be resolved within only a few light years of each other. Such features have been studied extensively using the Hubble Space Telescope and other high-resolution instruments which can separate individual structures that ground-based telescopes blur into a single glow. The discovery of the double nucleus was at first puzzling, because it seemed unlikely that two separate star clusters could remain so close without merging. Careful analysis showed that the apparent duplication is not a coincidence, but a natural result of stellar orbits influenced by the gravity of the central black hole. The stars in the eccentric disk move along elongated orbits. Because of their orbital alignment, many of them slow down at one side of their paths, spending more time there, and creating a concentration of light that appears as one peak of the double nucleus. The true dynamical centre occupied by the black hole lies closer to the other peak, which is somewhat fainter. The combination produces the illusion of two nuclei, but in reality, it is a single stellar disk viewed in projection. This discovery provided a direct window into the dynamical processes at the heart of Andromeda, confirming that collective orbital behavior can generate structures that appear at first glance to be distinct physical entities. The black hole itself is invisible, yet its mass can be measured through its gravitational influence. Stars close to the nucleus move at remarkable speeds, some hundreds of kilometers per second. By tracking their velocities, astronomers can calculate the mass required to hold them in orbit. The result is a mass far greater than that of any star cluster, confirming the presence of a supermassive black hole. Unlike the black holes in active galaxies that produce brilliant quasars, Andromeda's central black hole is relatively quiescent. It does not currently accrete large amounts of gas, so it lacks the luminous accretion disk and powerful jets seen in more active systems. Nevertheless, occasional X-ray flares have been detected from the region, hinting that small amounts of material do fall in from time to time. The nucleus also hosts a population of stars of varying ages. Most are old, consistent with the general bulge population, but observations in the ultraviolet reveal clusters of much younger stars as well. These young populations likely formed when gas funneled inward by the bar or spiral arms accumulated near the centre and triggered new star formation. The contrast between ancient stars orbiting in random paths and compact groups of young hot stars illustrates the continuing dynamism of the galactic core. Even in a region dominated by an enormous black hole, this cycle of star birth and death continues, though at a more modest level than in the outer spiral arms. The presence of the double nucleus also makes Andromeda an important laboratory for testing theories of galactic centers. Few nearby galaxies exhibit such a clearly resolved eccentric disk. The ability to study it in detail has provided models for how stars orbit close to supermassive black holes and how such systems maintain stability. The eccentric disk in Andromeda suggests that gas driven inward in the past formed a stellar disk, whose orbits gradually aligned under the black hole's gravity. Over time, dynamical friction and resonant interactions preserved the eccentric configuration, giving rise to the twin peaks observed today. This insight adds to the broader understanding of how central black holes and nuclear star clusters co-evolve within galaxies. The mass of Andromeda's black hole is significant when compared with that of the Milky Way. Our own galaxy harbours a black hole of about 4 million solar masses, far smaller than the one in Andromeda. This difference reflects variations in bulge size, since evidence suggests a close correlation between the mass of a galaxy's bulge and the mass of its central black hole. Andromeda's bulge is more massive than that of the Milky Way, and its black hole is correspondingly larger. This scaling relationship is one of the most important empirical results in modern astrophysics, showing that black holes and galaxies grow together in connected processes. In addition to stars, the nucleus contains diffuse gas. Observations in infrared and X-ray wavelengths reveal traces of hot and cold gas orbiting near the black hole. The amounts are small, but their presence indicates that some inflow continues. The lack of strong accretion signals suggests that either the supply is limited, or that feedback processes prevent gas from falling directly into the black hole. Stellar winds from young stars, supernova explosions and turbulence all contribute to shaping the nuclear environment. This delicate balance of supply and inhibition determines the current low luminosity state of Andromeda's black hole. The stability of the nuclear region depends on the interplay between gravitational forces and the collective behavior of stars. Models show that the eccentric disk can remain stable for hundreds of millions of years if the orbits are aligned in a coherent way. Any significant perturbation, such as a strong inflow of new stars or gas, could disrupt the structure, but for now it persists as one of the most remarkable features of the galaxy. The nucleus therefore stands as a snapshot of long-term, dynamical equilibrium, a system shaped by past events but still stable in the present. From a broader perspective, the central region of Andromeda highlights the importance of galactic nuclei in cosmic evolution. The black hole anchors the dynamics, the bulge provides a massive reservoir of stars, and the nuclear disk organizes stellar orbits into coherent structures. Each element interacts with the others, forming a system more complex than a simple glowing point. By observing the nucleus in detail, astronomers gain insight not only into Andromeda, but also into the general processes that govern galaxies across the universe. The lessons drawn here extend outward, providing templates for interpreting more distant systems that cannot be resolved with such clarity. The nucleus of the Andromeda Galaxy is therefore not merely the brightest part of the galaxy, but also one of its most scientifically rich regions. Within a space only a few light years across, it encapsulates the interplay of stars' gas and a supermassive black hole, illustrating principles of gravity and dynamics that apply across the cosmos. Its apparent double nucleus, its eccentric stellar disk, its central black hole, and its mixed populations of stars all contribute to a portrait of a galactic center that is both extraordinary and instructive. In the calm glow seen from Earth lies a place of extreme density and complexity, quietly demonstrating the universal processes that shape galaxies at their hearts. The stellar populations of the Andromeda Galaxy provide one of the clearest windows into its long history. By studying the colours, luminosities and chemical compositions of stars across the bulge disk and halo, astronomers reconstruct the sequence of star formation events that built the galaxy over billions of years. The central bulge contains predominantly old stars, many with ages greater than 10 billion years. These stars tend to be metal-rich, meaning they contain substantial amounts of elements heavier than hydrogen and helium. Such enrichment points to early and rapid star formation, during which repeated cycles of stellar death and supernova explosions quickly raised the chemical abundance of the interstellar medium. The smooth light of the bulge therefore records the earliest epochs of Andromeda's growth. Moving outward into the disk, the stellar population becomes more diverse. The inner regions still contain many older stars, but the spiral arms and the prominent star-forming ring are filled with much younger populations. Ultraviolet surveys reveal clusters of blue stars only a few million years old, while infrared images highlight the more diffuse populations of intermediate-age stars. The mix creates gradients in both age and metallicity across the disk. Generally, the inner disk is more metal-rich, reflecting the greater number of stellar generations that have enriched the gas there. The outer disk, by contrast, shows lower metallicity, suggesting that star formation has proceeded more slowly and with fewer cycles of enrichment. This radial gradient is one of the strongest indicators of how star formation and chemical evolution differ across galactic environments. In the very outermost regions of the disk, individual red giant stars can be resolved with large telescopes. These stars serve as excellent tracers of population age and metallicity. Observations with the Hubble Space Telescope and large ground-based observatories show that many of these outer stars are older and more metal-poor, consistent with a history of slower star formation and possible accretion from smaller companion galaxies. The ability to resolve individual stars at such distances is remarkable, made possible because of Andromeda's proximity compared to most other galaxies. This closeness allows detailed population studies that would be impossible in more distant systems. The halo of Andromeda, extending far beyond the visible disk, contains some of the oldest stars in the galaxy. Many are metal-poor, indicating that they formed early in the universe from gas that had not yet been significantly enriched. The halo also contains numerous globular clusters, dense spherical groups of hundreds of thousands of stars. These clusters are ancient, often with ages exceeding 12 billion years, and their compositions reveal the early conditions of star formation in the galaxy. Some globular clusters in the halo appear to have been accreted from smaller galaxies, as their chemical signatures differ from those of clusters that likely formed within Andromeda itself. This mixture highlights the role of mergers and accretion in building up the galaxy's stellar populations. Stellar metallicity gradients across the galaxy provide particularly important evidence for its formation history. Metallicity increases toward the center, reflecting the greater efficiency of enrichment in regions of high star formation. The gradient is not perfectly smooth, however. Discontinuities suggest episodes of accretion in which stars from satellite galaxies with different chemical histories were added to the mix. By mapping these gradients in detail, astronomers can identify where Andromeda's own stars dominate and where external contributions have altered the population. These analyses are sometimes referred to as galactic archaeology, since they use present-day evidence to reconstruct past events. Another layer of insight comes from stellar kinematics. By measuring the motions of stars, astronomers can distinguish populations that belong to different components of the galaxy. Disk stars tend to follow ordered rotation around the center, while bulge stars move more randomly, and halo stars often follow elongated orbits influenced by past accretion. Combining motion with metallicity reveals correlations. For example, metal-poor halo stars tend to have higher velocity dispersions, consistent with origins in disrupted satellites. These combined datasets provide a multidimensional view of Andromeda's stellar content far richer than what is possible from a simple image. Studies of variable stars add further detail. Cepheid variables which pulsate with periods linked to their luminosities have been used to measure distances within Andromeda and to identify younger populations. Lyrae variables, older pulsating stars typically found in globular clusters, trace ancient populations more than 10 billion years old. The presence and distribution of these variables reinforce the picture of a galaxy with multiple layers of stellar history from the earliest epochs to the present. Each type of star acts as a chronometer recording a specific time in the galaxy's evolution. The interplay between different stellar populations demonstrates how Andromeda has grown through both internal processes and external influences. Internally, star formation proceeded rapidly. In the bulge, slowed in the outer disk and continues today in the ring and arms. Externally, mergers with smaller galaxies contributed fresh stars and clusters, especially to the halo. The result is a mosaic of populations that together form one coherent system. This mixture makes Andromeda an ideal target for testing models of galaxy formation, since it embodies both the smooth growth of a large spiral and the irregular contributions of hierarchical assembly. One striking feature revealed by population studies is the sheer number of distinct stellar streams in the halo. These streams are composed of stars torn from disrupted satellites, and their compositions often differ from those of native Andromeda stars. Their presence highlights how much of the halo population may have originated outside the galaxy. In this way, the halo acts as a repository of evidence for past interactions with stellar metallicities and ages, serving as forensic tools to trace their origins. Each stream preserves information about the parent galaxy that was absorbed into Andromeda, making the halo a natural archive of galactic history. The overall balance of populations also underscores the importance of feedback processes. Supernova and stellar winds from massive stars enrich the interstellar medium with heavy elements, raising the metallicity of subsequent generations. The rate at which this occurred depended on the local star formation intensity. In the bulge, where star formation was initially rapid, enrichment was swift, leading to high metallicities. In the outer disk, slower star formation allowed metallicity to remain low for longer. This interplay creates the gradients we observe today, gradients that are central to understanding the timing and efficiency of galactic growth. The diversity of stellar populations in Andromeda makes it a benchmark for comparison with other galaxies. Because it is close enough for individual stars to be resolved, it provides a reference against which more distant galaxies can be interpreted. Population gradients, metallicity distributions, and stellar kinematics observed in Andromeda guide the interpretation of integrated light measurements in galaxies too far away to resolve. In this way, Andromeda serves as both a unique subject of study and a standard for extragalactic astronomy as a whole. Ultimately, the stars of Andromeda reveal a history written in light and chemistry. Each population, bulge stars, disk stars, young clusters, halo stars, and globular clusters, contributes a piece of the story. Together they show how the galaxy formed, early grew through continuous star formation, and was shaped by the accretion of smaller systems. By examining these populations carefully, astronomers not only reconstruct the history of a single galaxy, but also gain insight into the general processes that govern galaxy formation and evolution throughout the universe. Among the many stellar systems contained within the Andromeda Galaxy, the clusters stand out as particularly important for understanding how stars form, evolve, and assemble into larger structures. Andromeda hosts hundreds of globular clusters, which are dense spherical collections of hundreds of thousands of stars bound tightly by gravity. It also contains countless open clusters, which are looser associations of young stars located primarily in the spiral arms and the star-forming ring. Together, these clusters provide both ancient records of the galaxy's earliest history and living laboratories of ongoing stellar birth. By studying them in detail, astronomers can reconstruct the timeline of Andromeda's formation and the processes that continue to shape it today. The globular clusters of Andromeda are especially remarkable in number and diversity. Surveys have identified more than 400 confirmed clusters, with additional candidates still under study. This population is larger than that of the Milky Way, making Andromeda one of the richest known systems in terms of globular clusters. Many of these clusters orbit far out in the galactic halo, some at distances of more than 100,000 light-years from the centre. Their ages are generally greater than 10 billion years, placing their formation in the early universe not long after galaxies themselves first assembled. By analysing the light of these clusters, astronomers can determine their metallicities, revealing whether they formed from gas that was already enriched by earlier generations of stars or from more pristine material. The globular clusters show a wide range of metallicities, with some very metal-poor clusters likely formed in the earliest epochs, and others more metal-rich, perhaps captured from accreted satellite galaxies. Their spatial distribution is also revealing. Metal-poor clusters tend to populate the outer halo, while metal-rich ones are more common in the inner regions. This distribution suggests a layered history, in which some clusters formed within Andromeda itself, and others were acquired through mergers and accretion. Each cluster can therefore be thought of as a fossil preserving conditions from a specific moment in galactic history. The structure of the globular clusters themselves is dense and stable. Stars within them orbit in a compact volume with typical sizes only a few tens of light-years across, despite containing hundreds of thousands of stars. The high density means that stellar interactions are common, and in some cases exotic objects such as millisecond pulsars and blue straggler stars are found. These unusual stars are thought to form through close encounters and mergers in the crowded environments of the clusters. Observations of Andromeda's globular clusters, while limited by distance compared to those in the Milky Way, still reveal these dense cores and their role as environments of intense stellar dynamics. In contrast to the ancient globular clusters, the open clusters of Andromeda are young and transient. They are found primarily in the spiral arms and in the star-forming ring, where giant molecular clouds collapse to form groups of stars. Open clusters typically contain a few hundred to a few thousand stars loosely bound and easily dispersed over time. Their ages range from only a few million years to a few 100 million years, much younger than the globulars. Because their stars share a common age and chemical composition, open clusters serve as excellent laboratories for studying stellar evolution. By comparing clusters of different ages across the disk, astronomers can trace the progression of star formation over recent galactic history. The panchromatic Hubble Andromeda Treasury Survey has been instrumental in cataloguing thousands of star clusters in Andromeda. By imaging a large swath of the galaxy at high resolution across multiple wavelengths, this survey identified clusters of all ages and sizes. Some of the clusters are compact and well-defined, while others are diffuse associations that blend into the background. The survey revealed that star clusters are far more numerous than once thought, especially at the lower mass end where they dissolve quickly into the surrounding disk. This census provides a statistical foundation for understanding how often clusters form, how long they survive, and how they contribute to the stellar population of the galaxy. The distribution of clusters across Andromeda reflects the underlying structure of the galaxy. Open clusters trace the spiral arms and the star-forming ring marking, where molecular clouds are actively forming stars. Globular clusters trace the halo stretching far beyond the visible disk and connecting to the extended stellar streams left by disrupted satellites. Some globular clusters are even associated with these streams, reinforcing the idea that they were captured from smaller galaxies during past accretion events. In this way, clusters provide both a current and a historical map of galactic activity. The chemical properties of the clusters also offer insight into Andromeda's evolution. Spectroscopic studies of globular clusters show that their metallicities vary widely, with evidence for multiple populations even within individual clusters. This diversity indicates that globular clusters may have undergone complex formation histories with multiple episodes of star formation and enrichment. Open clusters, being younger, generally reflect the metallicity of the local interstellar medium at the time of their birth. By comparing their compositions across the disk, astronomers can chart how metallicity varies with radius and how it has changed over recent timescales. These measurements provide constraints on models of chemical evolution and star formation in large spiral galaxies. Another dimension of cluster studies involves their dynamics. The orbits of globular clusters in the halo reveal information about the gravitational potential of Andromeda. By mapping their motions, astronomers can trace the distribution of dark matter on large scales. Some clusters follow smooth elliptical orbits round the galaxy, while others appear to be on more chaotic paths consistent with origins in disrupted satellites. The velocity distributions of these clusters therefore serve as traces of the mass and shape of the dark halo. Open clusters, by contrast, orbit within the disk and disperse relatively quickly. Their dynamics are simpler, but still useful for probing the local gravitational environment of the spiral arms. The sheer number of clusters in Andromeda also underscores its scale compared to the Milky Way. With more than 400 confirmed globular clusters, Andromeda possesses nearly double the number found in our galaxy. This richness may be linked to its larger mass and to a more active history of mergers and accretion. The abundant globular population provides a vast archive of information about the conditions of early star formation in the local group. Each cluster contributes a piece of evidence to the broader picture of Andromeda's assembly. Through these many strands of evidence, the clusters of Andromeda form a bridge between past and present. The globular clusters preserve the ancient record of the galaxy's earliest formation stages, while the open clusters record the ongoing processes of star formation in the disk. Together they show that Andromeda is not a static system, but a dynamic one where new generations of stars are continually added, even as the remnants of the earliest generations still orbit in the halo. The study of these clusters not only deepens our understanding of Andromeda itself, but also provides a foundation for interpreting star cluster populations in more distant galaxies where such detail is not yet visible. Among the most striking features of the Andromeda Galaxy are its two prominent companions designated M32 and M110. These galaxies orbit within the gravitational field of Andromeda and show signs of having been shaped by their interaction with their massive host. Their presence demonstrates that galaxies are rarely isolated systems. Instead, they are embedded within networks of companions, streams and halos that interact over cosmic timescales. M32, the closer and more compact of the two, is classified as a compact elliptical galaxy. Despite its small size, it is unusually dense, containing a bright concentration of stars in a body only a few thousand light-years across. Its stellar population consists largely of old metal-rich stars, indicating that it has experienced a complex evolutionary history. The most widely accepted interpretation is that M32 was once a larger galaxy, whose outer layers were stripped away by tidal forces during past encounters with Andromeda. The dense core that remains is what we see today. Evidence for this scenario comes from its high central density, its lack of extended outer structure, and its metallicity, which is more typical of larger galaxies. M32's proximity to Andromeda has made it a subject of detailed study. It lies projected against the disk of Andromeda itself, so distinguishing its stars from those of the larger galaxy requires careful measurements. High-resolution imaging from the Hubble Space Telescope has resolved individual stars within M32, allowing astronomers to determine their ages and metallicities. These studies show that M32 contains both ancient populations and younger stars, suggesting that episodes of star formation may have continued even after it was tidally stripped. Some models propose that gas funneled into its centre during interactions with Andromeda may have fueled bursts of star formation in its compact core. The result is a galaxy that, although small, records both violent interactions and continuing evolution. M110, in contrast, is a dwarf elliptical galaxy with a more diffuse structure. It is larger in extent than M32 but far less dense, with a faint elongated shape. Unlike M32, M110 shows evidence of recent star formation, as indicated by the presence of young stars and dust lanes. These features suggest that M110 retains some interstellar material, which is unusual for dwarf elliptical galaxies since they are often stripped of gas during interactions with larger systems. M110's stellar populations include both old stars and intermediate-age stars, reflecting a more extended history of star formation compared to M32. The galaxy's morphology also shows signs of tidal disturbance. Subtle distortions in its outer isophotes and the presence of faint stellar streams suggest that gravitational interactions with Andromeda have shaped its current form. The roles of M32 and M110 in the history of Andromeda extend beyond their current appearances. Their interactions likely contributed to the formation of features in Andromeda's disk, such as the warp of the outer regions and possibly the formation of the star-forming ring. Simulations of galactic dynamics show that the passage of a satellite galaxy through the disk of a larger one can generate waves and resonances that shape the distribution of gas and stars. While the exact histories of M32 and M110 are still debated, their proximity and distorted structures strongly imply that they have played a role in Andromeda's ongoing evolution. M32 in particular provides a valuable case for understanding compact elliptical galaxies as a class. These galaxies are rare, and M32 is the closest known example. Its origin through tidal stripping supports the idea that compact ellipticals are remnants of larger systems reduced by interactions. Detailed study of M32 therefore offers insights into processes of galactic transformation that cannot be observed directly in more distant systems. Similarly, M110 illustrates how dwarf ellipticals can retain gas and continue forming stars under the influence of a massive neighbour. Each companion adds a dimension to our understanding of how large galaxies interact with and reshape their satellites. The orbits of M32 and M110 are not precisely known since measuring three-dimensional motions at such distances remains challenging. However, proper motion measurements combined with radial velocities provide constraints. These suggest that both galaxies are gravitationally bound to Andromeda, and are likely to have made close passages in the past. Such passages would have subjected them to strong tidal forces stripping stars and gas, and inducing disturbances in Andromeda's disk. The signatures of these encounters may be recorded in the stellar streams observed throughout Andromeda's halo, some of which could contain material once belonging to M32 or M110. The relationship between Andromeda and its companions also demonstrates the hierarchical nature of galaxy formation. Large galaxies grow not only by forming stars internally, but also by accreting smaller systems. The remnants of these processes are seen both in the distorted satellites themselves and in the debris they leave behind. In this context, M32 and M110 represent different stages of interaction, one stripped to a dense core, the other still diffuse but disturbed. Both are laboratories for studying how galaxies evolve under the gravitational dominance of a massive neighbour. Observations of M110 in particular have challenged the assumption that dwarf ellipticals are uniformly old and quiescent. Its ongoing star formation and dust content suggest that it has managed to retain interstellar material despite its proximity to Andromeda. This may be due to a relatively gentle interaction history compared to M32 or to the specific orbital path it has followed. Whatever the cause, M110 demonstrates that the evolutionary pathways of dwarf satellites are varied and complex. Its mixed populations of stars provide a record of star formation extending from the early universe to relatively recent times. M32's compactness, on the other hand, raises questions about the survival of central structures during tidal stripping. Despite losing much of its outer envelope, M32 retains a dense core with high central surface brightness. This suggests that the inner regions of galaxies are resilient to tidal disruption, preserving their identities even after dramatic encounters. The survival of such a core provides direct evidence for the robustness of galactic centers, which may remain intact long after the surrounding material has been dispersed into the halo of the larger galaxy. Together, M32 and M110 illustrate the variety of outcomes that interactions between galaxies can produce. One has been compressed into a compact elliptical, while the other remains a diffuse dwarf with traces of gas and dust. Both orbit within the gravitational influence of Andromeda, and both have contributed to shaping its structure through tidal forces and the transfer of material. Their contrasting states highlight the complexity of galactic evolution and the importance of environment in determining the fate of small galaxies. By examining these companions closely, astronomers gain not only knowledge of Andromeda's immediate environment, but also broader insight into the processes that shape galaxies throughout the universe. The lessons learned from M32 and M110 inform our understanding of satellite-host interactions, tidal stripping star formation in dwarfs, and the resilience of galactic cores. Within the quiet glow of Andromeda's companions lies a story of gravitational encounters, transformations, and survival, all of which contribute to the larger narrative of how galaxies assemble and evolve. Surrounding the Andromeda Galaxy are a series of faint but striking stellar streams and tidal debris fields that reveal its history of accretion and interaction. These features are not immediately visible in short exposure photographs, but long exposures with sensitive instruments show arcs, shells, and filaments of stars extending far beyond the bright disk. The most prominent of these is known as the Giant Stellar Stream, a vast ribbon of stars stretching tens of thousands of light years into the halo. This stream is believed to be the remnant of a dwarf galaxy that was torn apart by Andromeda's gravity in the relatively recent past, perhaps within the last few billion years. Its stars now orbit in elongated paths tracing the remains of the parent system, while slowly mixing with the broader halo population. The The discovery of the giant stellar stream came from wide-field surveys that imaged Andromeda's outskirts with unprecedented depth. These surveys revealed not only the stream itself, but also a host of smaller substructures, arcs looping around the disk shells of stars piled up at orbital turning points, and faint extensions pointing outward into intergalactic space. Together, these features demonstrate that Andromeda is still actively assembling mass through the disruption of smaller companions. The streams act as visible fossils of hierarchical galaxy formation, showing that the process is not confined to the distant past but continues into the present era. The stars in the giant stellar stream are relatively metal-rich compared to the background halo, suggesting that the progenitor galaxy was fairly massive for a dwarf. Its disruption would have contributed not only stars but also globular clusters and possibly gas to Andromeda's halo. Numerical simulations reproduce the observed shape of the stream by modelling the orbit of a satellite plunging through Andromeda's disk. These models indicate that the encounter was energetic, passing close to the centre and creating tidal tails that we now observe as extended arcs. The alignment of the stream with certain globular clusters and stellar overdensities further supports the scenario of a disrupted dwarf system. Beyond the giant stellar stream, Andromeda's halo is laced with other substructures. Some appear as faint loops or plumes of stars wrapping around the disk, while others are more diffuse clouds scattered across the halo. Each is thought to represent material stripped from a satellite galaxy, either during a single encounter or over repeated passages. In some cases, the stellar streams can be linked to known satellites, while in others the progenitors are no longer identifiable. These features demonstrate that the halo is not a smooth distribution of stars, but a patchwork of remnants from many different sources. The outer halo is particularly rich in such structures. Surveys have traced individual stars out to distances of several 100,000 light-years, revealing an extended and irregular envelope. Within this envelope lie streams that cross each other's shells, where stars have piled up, and clumps that may be the last remains of ancient satellites. The complexity of the halo suggests that Andromeda has undergone numerous mergers throughout its history, each leaving behind imprints that have yet to be fully mixed. Over billions of years, these features will gradually disperse, but for now they provide a rare opportunity to study galactic accretion in action. Globular clusters are often associated with these streams, reinforcing the idea that they were once part of accreted galaxies. Several clusters in Andromeda's halo are located along the giant stellar stream, suggesting they were carried in with the progenitor. Their metallicities and stellar populations sometimes differ from those of Andromeda's native clusters, providing additional evidence for external origin. By mapping the positions and velocities of these clusters, astronomers can reconstruct the orbits of the disrupted systems and better understand the gravitational potential of Andromeda itself. The study of stellar streams is aided by the ability to resolve individual stars in Andromeda. Large telescopes can distinguish red giant stars at these distances, allowing astronomers to measure their brightness and colour. These measurements provide information on the ages and metallicities of the stream populations, which in turn reveal the nature of the progenitor galaxies. The streams often contain stars of intermediate age and relatively high metallicity, consistent with origins in dwarf galaxies that had significant histories of star formation before disruption. Such data allow astronomers to connect the debris we see today with the galaxies that once contributed them. The motions of stars in the streams are also critical. Spectroscopic surveys measure the radial velocities of individual stars, providing constraints on their orbits. By combining these measurements with models, astronomers can infer the shape of Andromeda's dark matter halo, since the stars move under its gravitational influence. The distribution and dynamics of the streams therefore serve as probes of both Andromeda's history and its invisible mass. This dual role makes them among the most valuable features for understanding the galaxy at large. The giant stellar stream in particular has been modelled extensively. Some simulations suggest that its progenitor may have been a satellite as massive as the current Triangulum galaxy, though most estimates place it as somewhat smaller. The stream's extent and alignment imply that the encounter was relatively recent astronomically speaking, since the debris has not yet fully dispersed. The stream passes behind Andromeda as seen from Earth, curving outward into the halo before wrapping back toward the disk. This three-dimensional structure has been mapped by measuring distances to individual stars within the stream, a challenging task that requires precise photometry and the use of standard candles such as red giant branch stars. The presence of multiple streams and shells indicates that Andromeda's growth has been continuous and varied. Some accretions involved relatively large satellites producing prominent features, while others were smaller and left subtler imprints. Together they demonstrate the hierarchical nature of galaxy formation, in which large galaxies grow by consuming many smaller ones. Andromeda's halo, rich with substructure, provides direct evidence for this process in the local group. The streams also raise questions about the fates of dark matter halos of the progenitor galaxies. While the stars form visible streams, the dark matter would have been stripped and dispersed as well, blending into Andromeda's own halo. These events therefore contribute not only visible stars but also invisible mass altering the gravitational potential of the galaxy. Understanding this process is essential for connecting observations with theoretical models of galaxy evolution. Another notable feature of Andromeda's outskirts is the presence of shells, where stars appear piled up at certain radii. These shells are created when stars from a disrupted satellite reach the apocenters of their orbits, slowing down and creating overdensities. Multiple shells at different radii can result from repeated oscillations of debris within the gravitational potential. The identification of shells in Andromeda adds to the evidence of ongoing accretion and provides specific markers of past events. Taken together, the stellar streams and tidal debris of Andromeda present a vivid portrait of a galaxy still in the process of assembly. They show that even a massive spiral galaxy already containing hundreds of billions of stars is not a finished structure, but an evolving one. Each arc plume and shell is a reminder of a smaller galaxy that once orbited independently and is now part of Andromeda's growing halo. Through careful observation and modelling, astronomers use these features to reconstruct the complex dance of interactions that has shaped Andromeda's present form. The motions of stars and gas within the Andromeda Galaxy reveal the underlying distribution of mass, and they provide some of the clearest evidence for the presence of dark matter. When astronomers first measured the rotation of Andromeda, they expected to find that stars and gas far from the centre would orbit more slowly than those closer, inasmuch as planets in the solar system move faster when nearer to the Sun and slower when farther away. Instead, the measurements showed that Andromeda's rotation curve remains nearly flat at large radii, meaning that stars tens of thousands of light-years from the centre orbit at almost the same speed as those much closer in. This result could not be explained by the gravitational pull of visible stars and gas alone. The implication is that an unseen halo of dark matter surrounds the galaxy, providing the additional gravity required to keep the outer stars bound at such speeds. The rotation curve of Andromeda has been studied extensively using multiple tracers. In the inner regions, the motion of stars and ionized gas can be measured with optical spectroscopy, providing velocities along the line of sight. In the outer disk, neutral hydrogen gas emits the 21 centimeter radio line, which can be mapped with radio telescopes to trace motions well beyond the visible edge of the galaxy. Even farther out, the velocities of globular clusters and satellite galaxies provide constraints on the mass at larger radii. All of these observations converge on the conclusion that Andromeda is embedded in a massive dark matter halo extending far beyond the luminous disk. Estimates of the total mass of Andromeda vary partly because different methods probe different regions and rely on different assumptions. Most measurements suggest a total mass between 1 and 2 trillion times the mass of the Sun, with dark matter accounting for the vast majority of it. The uncertainties arise from the difficulty of measuring motions at extreme distances and from the fact that the halo is not directly visible. Nevertheless, the consensus is that Andromeda is one of the most massive members of the local group, comparable to, or perhaps somewhat more massive than the Milky Way. The dark matter halo not only explains the flat rotation curve, but also influences the shapes of the stellar streams and the motions of satellite galaxies. Numerical simulations show that the paths of disrupted satellites depend strongly on the mass and shape of the dark matter halo. By matching observed streams such as the giant stellar stream to simulated orbits, astronomers can constrain the halo's properties. Some studies suggest that Andromeda's halo may be elongated rather than perfectly spherical, while others emphasize the uncertainties in such reconstructions. The precise shape remains a matter of debate, but the evidence is clear that the halo dominates the galaxy's mass. The inner regions of Andromeda also reveal interesting dynamics. The bulge stars move in random directions, producing broad velocity dispersions, while the disk stars follow more ordered circular orbits. The transition between these components can be traced through spectroscopy, providing insight into how the bulge and disk interact. Gas in the spiral arms and the star-forming ring shows non-circular motions influenced by the bar with inflows and outflows that redistribute angular momentum. These kinematic signatures demonstrate that even within the disk, the motions are not simple circles, but are shaped by resonances and gravitational interactions. The study of planetary nebulae within Andromeda provides another window into stellar motions. Planetary nebulae are shells of gas ejected by dying stars, and their bright emission lines make them relatively easy to observe even at great distances. By measuring the Doppler shifts of these lines, astronomers can determine the velocities of the nebulae and thus of their parent stars. Surveys of planetary nebulae across Andromeda's disk and halo have provided detailed maps of stellar motions, reinforcing the picture of a flat rotation curve and an extended dark halo. Globular clusters too serve as tracers of the gravitational potential. Their positions and velocities at large distances from the galactic center reveal the pull of the halo far into the outskirts. Some clusters move along paths consistent with association to stellar streams, while others follow more isolated orbits. By compiling velocities for many clusters, astronomers can estimate the mass enclosed within their distances. These estimates consistently point to a massive halo extending hundreds of thousands of light years. The presence of dark matter is not unique to Andromeda, but its proximity makes it an ideal system for study. The combination of resolved stars, extended gas, and numerous clusters provides a wealth of traces unmatched in more distant galaxies. The ability to map these motions in detail allows astronomers to test models of dark matter distribution, contributing to the broader effort to understand this mysterious component of the universe. While the exact nature of dark matter remains unknown, its gravitational influence on galaxies like Andromeda is undeniable. The motions of satellite galaxies around Andromeda also contribute to the picture. M32, M110 and more distant dwarfs orbit within the halo, and their velocities provide constraints on the total mass. Some satellites show signs of being on elongated orbits, while others appear to be bound in more circular paths. The diversity of these orbits reflects both the mass distribution of the halo and the varied accretion histories of the satellites. Modelling these motions remains challenging, but as measurements improve, they provide valuable checks on mass estimates derived from the rotation curve. Beyond simply measuring mass, the study of motions within Andromeda illuminates processes of galactic evolution. The flat rotation curve demonstrates the dominance of dark matter, while deviations from circular motions show how bars and spiral density waves redistribute angular momentum. Stellar streams reveal the orbits of disrupted satellites and constrain the halo's shape. Planetary nebulae and globular clusters act as precise markers of the gravitational potential. Together, these elements provide a dynamic portrait of a galaxy whose structure is shaped not only by visible stars and gas, but also by an immense unseen halo. The importance of Andromeda's rotation curve cannot be overstated. It was among the first galaxies in which a flat rotation curve was clearly observed, contributing to the recognition that dark matter must exist on galactic scales. This insight, first solidified in the late 20th century, has since become a cornerstone of cosmology. Andromeda, visible to the naked eye as a faint smudge in the sky, thus played a pivotal role in uncovering one of the deepest mysteries of modern astrophysics. Today, ongoing surveys with radio telescopes, optical spectrographs, and space-based instruments continue to refine the measurements, pushing further into the halo and improving constraints on the distribution of mass. The study of motions within Andromeda therefore bridges local observations with cosmic questions. By examining the paths of stars, gas clusters, and satellites, astronomers uncover the invisible framework that holds the galaxy together. Dark matter, though unseen, reveals itself through the consistency of these motions. The rotation curve, the kinematics of streams, and the dynamics of companions all converge on the same conclusion. Andromeda is not simply a disk of stars, but a vast structure embedded in a massive extended halo. This understanding transforms a simple visual impression of a spiral galaxy into a deep recognition of the complex layered forces that govern its existence. Extending beyond the bright stellar disk of the Andromeda Galaxy is an immense circumgalactic medium, a diffuse envelope of gas that stretches hundreds of thousands of light-years into intergalactic space. This medium is invisible to the human eye, but its presence has been revealed through careful observations at ultraviolet and X-ray wavelengths. When the light from distant quasars passes through the circumgalactic medium of Andromeda, it leaves characteristic absorption lines in the spectrum showing that the intervening space is filled with ionized gas. These observations demonstrate that the environment of Andromeda is not empty, but instead contains a vast reservoir of material that interacts with both the galaxy itself and the broader local group. The circumgalactic medium is composed of multiple phases. One component is hot with temperatures of millions of degrees detectable through X-ray emission and absorption. This hot gas forms an extended halo that glows faintly, though too weakly to be seen without sensitive instruments. Another component is warm, consisting of ionized gas at temperatures of tens of thousands of degrees. This gas is traced by ultraviolet absorption lines of elements such as carbon, oxygen, and silicon. A third component is cool, made up of neutral hydrogen, that can be mapped through the 21 centimeter line at radio wavelengths. Together, these phases form a complex multi-phase medium that envelops the galaxy. Measurements suggest that the circumgalactic medium of Andromeda is enormous in scale. Studies using the Hubble Space Telescope's Cosmic Origins spectrograph have traced ionized gas out to distances of more than 1,000,000 light-years, nearly halfway to the Milky Way. This extent implies that the circumgalactic medium of Andromeda may overlap with that of our own galaxy, creating a shared reservoir of gas between the two. The total mass of this gas is thought to be comparable to, or even greater than, the mass of all the stars in Andromeda, making it a dominant component of the galaxy's baryonic matter budget. The circumgalactic medium plays a crucial role in galactic evolution. It acts as both a source and a sink of material. Gas from the intergalactic medium accretes into the circumgalactic halo and eventually falls into the galaxy-fueling star formation. At the same time, energetic processes within the galaxy, such as supernova explosions and stellar winds, expel gas outward into the halo. This cycling of material regulates the growth of the galaxy, controlling how much gas is available for star formation at any given time. The circumgalactic medium also serves as a reservoir of heavy elements produced in stars and spread outward by galactic winds. Observations show that metals are present far into the halo, evidence that Andromeda has enriched its environment over billions of years. One of the most striking findings about Andromeda's circumgalactic medium is its apparent structure. The gas is not distributed uniformly, but appears to be clumpy and filamentary. Absorption studies using multiple background quasars show variations in gas density and ionization from one sightline to another, suggesting that the halo contains filaments and clouds embedded in a more diffuse medium. These structures may be related to the inflow of intergalactic gas along cosmic filaments, or to the outflow of material driven by stellar feedback. The detailed geometry of the circumgalactic medium remains uncertain, but the evidence points to a dynamic and structured environment. The hot component of the halo is particularly significant for theories of galaxy formation. Simulations predict that galaxies as massive as Andromeda should be surrounded by corona of hot gas formed when infalling material is shock-heated to high temperatures as it encounters the galaxy's gravitational potential. Observations of X-ray emission around Andromeda support this prediction, though the signal is faint and difficult to separate from background sources. The existence of such a hot corona helps explain why galaxies do not continue to accrete gas at unlimited rates. The hot medium acts as a buffer, slowing the inflow of new material and regulating star formation over long time scales. The circumgalactic medium also interacts with Andromeda's satellites and stellar streams. As dwarf galaxies orbit through the halo, they experience drag from the surrounding gas, gradually losing momentum and spiraling inward. Gas within the dwarfs can be stripped away by the pressure of the circumgalactic medium quenching star formation and leaving behind gas-poor systems. Stellar streams moving through the halo may also be affected as their stars pass through regions of varying density and ionization. In this way, the circumgalactic medium connects the central galaxy to its extended environment, shaping not only Andromeda itself but also its companions. Studies of the chemical composition of the circumgalactic medium reveal that it contains significant amounts of oxygen and other heavy elements. These metals must have originated inside stars and been expelled into the halo by galactic winds and supernovae. The distribution of metals in the halo therefore provides a record of past feedback processes. The detection of enriched gas far from the disk indicates that Andromeda has been efficient at driving material outward, perhaps during earlier epochs of more intense star formation. This enrichment is important for understanding the cosmic cycle of matter, as metals ejected into the circumgalactic medium can eventually mix into the intergalactic medium and influence the formation of other galaxies. The overlap of the circumgalactic media of Andromeda and the Milky Way raises intriguing possibilities. If the halos extend as far as current evidence suggests, then the two galaxies may already share a common gaseous envelope. This would mean that long before their stellar disks interact, their gaseous halos have been influencing each other. Such an overlap could facilitate the exchange of material between the galaxies, blurring the distinction between their individual circumgalactic environments. It also provides a local example of how large galaxies embedded in the same group environment may affect one another even before direct collisions occur. The study of Andromeda's circumgalactic medium is still developing, with new instruments promising deeper insights. Future ultraviolet spectrographs, X-ray observatories and radio arrays will map the halo with greater resolution and sensitivity, revealing its structure in detail. For now, the existing evidence paints a picture of a vast, dynamic, multi-phase medium that is central to the life cycle of the galaxy. It is a hidden component invisible in direct images, but essential for understanding how galaxies acquire, retain, and lose their material. In Andromeda, the circumgalactic medium demonstrates that a galaxy is more than just the stars and gas seen in its disk. It is embedded within a vast environment that stretches nearly 1 million light-years, filled with hot, warm and cool gas that both feeds and is fed by the galaxy. This environment connects the visible structure of Andromeda to the larger cosmic web, linking the processes of star formation within the disk to the flows of matter across intergalactic space. By studying the circumgalactic medium, astronomers glimpse the broader context of galaxy evolution, where visible stars are only the surface of a much deeper and more extended system. Measuring the distance to the Andromeda Galaxy has been one of the most important challenges in modern astronomy, because it allows scientists to calibrate the scale of the universe. Andromeda is the nearest large spiral galaxy to the Milky Way, and establishing its distance with precision has been essential for turning relative measurements of cosmic size into absolute values. The task has been approached with multiple methods, each using a different type of star or stellar population as a standard candle. These measurements together converge on a distance of about 2.5 million light-years, though the exact figure has been refined many times over the past century. The first breakthrough came in the early 20th century, when astronomers began to identify Cepheid variable stars within Andromeda. Cepheids are luminous stars that pulsate with regular periods, and their brightness changes in a predictable way that links the length of the period to the intrinsic luminosity. By comparing the true luminosity inferred from the period with the observed brightness, astronomers can determine the distance. The discovery of Cepheids in Andromeda by Edwin Hubble provided decisive evidence that it is an external galaxy far beyond the Milky Way. This measurement ended the long debate over whether spiral nebulae were local objects or distant galaxies, establishing the existence of a universe filled with galaxies. Since then, Cepheids have continued to play an important role in refining the distance to Andromeda. Observations with the Hubble Space Telescope have identified large samples of Cepheids across its disk, allowing precise period luminosity relations to be applied. These measurements must account for the effects of dust which dims and reddens the light, as well as for metallicity differences that slightly alter the intrinsic brightness of Cepheids. By carefully calibrating these factors, astronomers have achieved distance estimates with uncertainties of only a few %. Another important method involves the tip of the red giant branch. In a population of old stars, red giants evolve upward in brightness until helium fusion ignites in their cores. This ignition occurs at nearly the same luminosity for all red giants, producing a sharp cutoff in the brightness distribution known as the tip of the red giant branch. By measuring the brightness of this tip in Andromeda's stellar populations, astronomers obtain a reliable distance indicator that is less affected by dust than Cepheids. Large telescopes have resolved individual red giants in Andromeda's halo, making this method particularly effective for measuring the distance with high precision. Eclipsing binary stars provide a completely different approach. In these systems, two stars orbit each other and periodically pass in front of one another as seen from Earth. By measuring the timing of the eclipses and the radial velocities of the stars, astronomers can determine their sizes, masses, and luminosities directly from physical principles. Comparing these intrinsic luminosities with observed brightness yields the distance. A small number of eclipsing binaries have been identified and studied in Andromeda, providing independent checks on other methods. The agreement between these binaries, Cepheids, and red giant branch measurements strengthens confidence in the overall distance scale. Planetary nebulae have also been used as distance indicators. The brightest planetary nebulae in a galaxy reach a nearly universal maximum luminosity. By constructing the luminosity function of planetary nebulae in Andromeda and comparing it with that of nearby galaxies, with known distances, astronomers can derive a distance estimate. This method is less precise than Cepheids or the red giant branch, but provides useful consistency checks. Similarly, the luminosity of the brightest globular clusters has been employed as a secondary distance indicator. While more uncertain, these methods add to the network of cross-checks that ensure reliability. The combined use of multiple methods is important because each has different strengths and vulnerabilities. Cepheids are luminous and easily detected but require correction for dust. The red giant branch is less affected by dust but requires resolving individual stars in faint outer regions. Eclipsing binaries provide direct physical measurements but are rare. By applying all of these techniques, astronomers reduce the chance that systematic errors will bias the result. The convergence of independent methods on a distance of about 2.5 million light-years gives confidence in the result. Light travel time adds another perspective. The photons arriving from Andromeda today began their journey long before humans evolved. A distance of 2.5 million light-years means that the light left Andromeda 2.5 million years ago. At that time, early human ancestors such as Australopithecus were just beginning to walk upright on Earth. This temporal perspective emphasizes the vast scale of space and time involved in extragalactic astronomy. When we observe Andromeda, we see it as it was in the distant past, not as it is at this moment. Accurate distance measurement to Andromeda is critical not only for its own sake, but also for the larger cosmic distance ladder. Cepheids in Andromeda can be used to calibrate more distant galaxies, observed with the same methods, and those galaxies in turn serve as hosts of supernovae that act as standard candles on even larger scales. The chain of calibration ultimately allows astronomers to measure the expansion rate of the universe known as the Hubble constant. In this way, the distance to Andromeda connects directly to one of the fundamental parameters of cosmology. Modern measurements continue to refine the figure. Distances are now often quoted with uncertainties of only a few %, a remarkable achievement given the challenges of observing individual stars in a galaxy millions of light-years away. The current consensus places the distance at about 775 kiloparsecs, which translates to roughly 2.5 million light-years. Ongoing surveys with the Hubble Space Telescope and the Gaia mission provide even more precise parallaxes and photometry, further tightening the calibration. These improvements ensure that the distance to Andromeda remains one of the most secure rungs on the cosmic distance ladder. The effort to measure Andromeda's distance illustrates how astronomical progress depends on multiple methods, careful cross-checking and incremental refinements. What began with the discovery of Cepheids nearly a century ago has expanded into a comprehensive set of techniques that together establish Andromeda as a cornerstone of extragalactic astronomy. Its proximity, brightness, and wealth of observable stars make it uniquely suited to this role. By anchoring the scale of the universe, the distance to Andromeda transforms a nearby spiral galaxy into a cosmic yardstick linking our immediate galactic neighbourhood to the vast expanse of the universe beyond. The study of the Andromeda Galaxy has advanced through a long history of observations, beginning with naked eye records and extending to the most sophisticated space telescopes of the present. Ancient skywatchers described Andromeda as a faint cloud-like patch in the constellation that bears the same name. The Persian astronomer al-Sufi documented it in the 10th century as a small nebulous feature. For centuries afterward, it remained little more than a curiosity, and star catalogues noted as a fuzzy spot without clear structure. The invention of the telescope in the 17th century brought the first significant changes. Early observers such as Simon Marius reported the extended oval shape of the nebula, noting its brighter centre and diffuse halo. Still, the true nature of the object was not understood. It was classified with other nebulae, a term then used broadly for any faint extended object. As telescopes improved, astronomers began to sketch Andromeda in greater detail. In the 18th and 19th centuries, observers like Charles Messier and William Herschel included it in their catalogues, with Messier assigning it the designation M31. These catalogues were intended in part to distinguish such objects from comets, which they might otherwise resemble in small telescopes. Herschel speculated about the possibility that nebulae might be collections of stars, but he could not resolve individual stars in Andromeda with the instruments of his time. The debate over the nature of spiral nebulae continued into the early 20th century, with some astronomers arguing that they were gaseous clouds within the Milky Way, and others suggesting they were island universes or galaxies beyond our own. The decisive breakthrough came in the 1920s, when Edwin Hubble identified Cepheid variable stars in Andromeda using the 100-inch telescope at Mount Wilson Observatory. By applying the period luminosity relation of Cepheids, he determined their distances and showed that they lay far beyond the Milky Way. This discovery resolved the so-called Great Debate in astronomy, proving that the universe is filled with galaxies beyond our own. From that point forward, Andromeda became recognized as the nearest large spiral galaxy and a key reference point for extragalactic research. Subsequent decades brought new tools and deeper insights. Photographic plates captured long exposures that revealed spiral arms, dust lanes, and satellite galaxies. Spectroscopy allowed the measurement of radial velocities, showing that Andromeda is moving toward the Milky Way rather than away from it. Radio astronomy opened another window, mapping the 21-centimetre line of neutral hydrogen and tracing the galaxy's rotation curve far beyond the visible disk. These observations provided the first compelling evidence for the presence of dark matter, as the rotation curve remained flat at large distances where the visible mass could not account for the motion. The space age transformed the study of Andromeda yet again. The Hubble Space Telescope, launched in 1990, provided high-resolution imaging capable of resolving individual stars across the galaxy. Surveys such as the panchromatic Hubble Andromeda Treasury mapped a large portion of the disk in exquisite detail, cataloguing hundreds of millions of stars. These observations allowed astronomers to construct color magnitude diagrams for different regions of the galaxy, reconstructing star formation histories with unprecedented precision. Hubble also revealed the double nucleus at the center, an eccentric disk of stars orbiting a supermassive black hole. Ground-based telescopes equipped with modern detectors and adaptive optics have complemented space-based work. The Keck Observatory, the Very Large Telescope, and others have measured the motions of stars, globular clusters, and satellite galaxies. Wide-field surveys such as the Pan-Andromeda Archaeological Survey mapped the faint outskirts of the galaxy, discovering streams, shells, and other debris from disrupted satellites. These features provided direct evidence of Andromeda's ongoing growth through mergers confirming predictions of hierarchical galaxy formation models. Radio and millimeter observatories have been essential for understanding the interstellar medium of Andromeda. The Atacama Large Millimeter and Submillimeter Array maps molecular gas clouds in the disk, identifying the birthplaces of new stars. Large single-dish radio telescopes trace the extended neutral hydrogen envelope and its warp linking the galaxy to its environment. Infrared observatories such as Spitzer and Herschel have revealed the dust distribution, showing the glowing star-forming ring and the complex patterns of absorption across the disk. Ultraviolet observatories have mapped the young stellar populations, highlighting the activity in the arms and the ring. Each wavelength adds another layer to the portrait of Andromeda, transforming it from a faint smudge into a richly detailed system. In recent years, the Gaia mission has provided precise astrometric data for stars in the Milky Way, and its reach extends even into Andromeda. Gaia measures the motions of stars with exquisite accuracy, allowing astronomers to refine models of the galaxy's structure and to better understand the orbits of its satellites. Combined with Hubble imaging, Gaia data enable three-dimensional reconstructions of Andromeda's halo streams, improving models of its mass distribution. These efforts continue to refine our understanding of the galaxy as an evolving dynamic system. The James Webb Space Telescope, launched in 2021, has begun to contribute to the study of Andromeda as well. Its infrared sensitivity allows it to peer through dust and resolve stellar populations in crowded regions near the center. Webb observations complement Hubble's optical data, providing new insights into star formation stellar populations and the role of dust in shaping the appearance of the galaxy. The combination of these space observatories with ground-based surveys ensures that Andromeda remains one of the most closely studied galaxies in the universe. Each generation of instruments has added depth and nuance to the picture. What was once a faint cloud is now known to be a sprawling spiral galaxy with a double nucleus, a supermassive black hole, a star-forming ring, hundreds of globular clusters, and an extended halo rich with streams and debris. The history of observation reflects the broader progress of astronomy itself, from naked-eye cataloguing to precision space-based measurements. Andromeda has been central to many milestones: the discovery that galaxies exist beyond the Milky Way, the recognition of dark matter, and the development of techniques for reconstructing galactic histories. The ongoing study of Andromeda also shows the value of collaboration across different domains of astronomy. Optical infrared, ultraviolet X-ray, and radio observations together create a multi-wavelength view that no single method could provide. Each reveals different components: stars, dust gas, hot plasma, and dark matter. Together they create a coherent model of a galaxy that is both a neighbor and a representative of spirals throughout the universe. As instruments continue to advance, Andromeda remains a prime target, offering both proximity and complexity. Its detailed observation enriches not only our understanding of a single galaxy, but also the principles that apply across billions of galaxies spread through the cosmos. Within the local group of galaxies, the Andromeda Galaxy occupies a position of dominance alongside the Milky Way, and understanding its place within this environment is essential for building a full picture of its present configuration. The local group is a gravitationally bound collection of more than 50 galaxies, ranging from the two giant spirals to many smaller dwarf ellipticals and irregulars. At its center of mass lie the Milky Way and Andromeda, each surrounded by their own systems of satellites and extended halos of stars and gas. The Triangulum Galaxy, a smaller spiral also plays a role, orbiting within the gravitational sphere of influence defined by these two giants. Together, these three galaxies form the primary structure of the local group, while the dwarfs populate the outer regions. Andromeda's position within this group is not isolated but highly interactive. Its halo overlaps in extent with the surrounding space, and its circumgalactic medium likely stretches close to or even into that of the Milky Way. The distribution of dwarf satellites around Andromeda is lopsided, with many concentrated in particular planes or alignments. This anisotropy may reflect the way in which dwarf galaxies were accreted along filaments of the cosmic web, funneled into Andromeda's potential well in groups, rather than as random individuals. Some satellites are clearly associated with stellar streams, their stars and clusters already being torn apart and incorporated into Andromeda's halo. Others remain intact, orbiting as companions for now, but subject to gradual disruption. The dynamics of the local group are still being measured, but evidence suggests that Andromeda and the Milky Way together contain the majority of its mass. Their dark matter halos dominate the gravitational field, binding the smaller galaxies in orbit around them. The total mass of the local group is estimated at several trillion times the mass of the Sun, with Andromeda contributing a significant fraction. The relative motion of Andromeda toward the Milky Way has been known since the early 20th century, measured by the blue shift of its spectral lines. This motion demonstrates that the galaxies are gravitationally bound. However, within the scope of this narrative, the emphasis remains on the current structure of the group, not predictions of future encounters. Within this shared environment, the Triangulum Galaxy, or M33, provides an important reference. It is smaller than both the Milky Way and Andromeda, with a mass perhaps 1/10 as large, but it is the third largest galaxy in the group. Observations show that Triangulum is itself connected to Andromeda through tidal interactions. Stellar streams and distortions in its outer disk suggest that it may have passed close to Andromeda in the past, though the details of this interaction remain debated. Its position illustrates the hierarchical relationships within the local group. Large spirals dominate, while smaller spirals and dwarfs orbit and interact around them. The dwarf galaxies associated with Andromeda provide insight into the processes of galaxy formation on the smallest scales. Some are compact ellipticals like M32, some are diffuse systems like M110, and many others are faint dwarfs with only a few million stars. These dwarfs are vulnerable to tidal stripping, and many show evidence of disruption. Their orbits are difficult to measure precisely, but mapping their positions and velocities with modern instruments is gradually revealing their structure. Some appear to align along coherent planes, suggesting that they may have been accreted as groups. Others are scattered more randomly, reflecting the stochastic nature of hierarchical growth. The local group as a whole is embedded within a larger structure, the local sheet, which in turn is part of the cosmic web of filaments and voids. Andromeda's location within this web has influenced its growth by guiding the flow of gas and dwarf galaxies along filaments. This context explains why the distribution of satellites is not uniform, but instead shows alignments. It also places Andromeda within the broader environment of nearby galaxy groups such as the Sculptor group and the MRD1 group, which together define the local region of the universe. Understanding Andromeda's place within this network helps astronomers connect small-scale observations with large-scale cosmological models. The relationship between Andromeda and the Milky Way is central to the structure of the local group. Their halos dominate the gravitational potential, and their satellites orbit within their spheres of influence. While each galaxy has its own distinctive properties, their combined presence defines the group as a whole. Their proximity allows detailed comparisons, highlighting both similarities and differences. Both are barred spiral galaxies, both host supermassive black holes, and both contain rich systems of globular clusters and satellites. Yet Andromeda is larger, with a more massive bulge and a more populous globular cluster system, while the Milky Way contains features such as the Magellanic Clouds that Andromeda lacks. The study of Andromeda in the context of the local group also provides benchmarks for theories of galaxy evolution. The evidence of stellar streams, satellite disruption, and circumgalactic medium enrichment all demonstrate how galaxies grow through accretion and interaction. By observing these processes in detail in Andromeda, astronomers calibrate models that are then applied to more distant systems. The local group is therefore not just a collection of galaxies, but a laboratory for understanding cosmic structure. Within it, Andromeda stands as the nearest large spiral other than our own, offering a complementary perspective on the processes that shape galaxies. Observations of the local group reveal that its galaxies are not static islands, but participants in a dynamic environment. Gas flows through the circumgalactic media of Andromeda and the Milky Way satellite's orbit, and are disrupted, and stars are exchanged between systems through tidal interactions. Each of these processes leaves signatures in the present-day structure. The distribution of metallicities in halo stars, the alignment of dwarf satellites, the shapes of stellar streams, and the enrichment of the circumgalactic medium all reflect the complex history of the group. Studying these features in Andromeda and comparing them with those in the Milky Way builds a more complete picture of how large galaxies assemble. In the current era, instruments such as Gaia Hubble and ground-based surveys continue to map the local group with increasing precision. Their data provide three-dimensional positions and velocities for star satellites and streams, refining our understanding of the gravitational field. These observations show that Andromeda's place in the local group is not merely as an isolated spiral, but as a central component of a dynamic network of galaxies bound together by dark matter. Its halo reaches outward into space, overlapping with those of its companions, and its satellites orbit in complex patterns shaped by billions of years of interaction. The context of the local group frames Andromeda not as a solitary galaxy, but as part of a larger structure defined by gravity gas and cosmic history. Its connections to satellites, to the Triangulum Galaxy, to the Milky Way, and to the cosmic web show that no galaxy exists alone. Each is part of an interwoven network with matter and energy flowing across scales from the smallest dwarfs to the filaments of the universe. By studying Andromeda within this setting, astronomers see not only the details of one galaxy, but also the principles of structure formation and cosmic organization. The galaxy thus serves as both a neighbor and a guide, helping us understand the broader universe through the lens of our local environment.